we did 12.3 was over the probability of a single event, which wasn't too bad. But now we're going to get into probability of multiple events. And so this is the stuff where it's the probability of if I roll a dice and flip a coin, what's the probability I roll a 4 and then flip heads? Or what's the probability that it is sunny outside, but it's also raining outside, or something like that. So there's 2 or 3. We're only going to. You can find the probability of all of that happening with some of this stuff. So the first thing, and this is, there's this one and then another one that is equally the hardest things I would say for today. Now, again, they're hardest in my opinion because I'm not super good with memorization like this. I get things flipped around when they're similar. So classifying events, there's the difference between dependent events and independent events. Dependent events is when the second event depends on the first event. That's not the best definition ever, or I should say more, that's not the official definition, but I think that's the best way to look at it. The reason it's called dependent is because the second event depends on the first event. So if you, well, that's not a good example. If I roll a dice, if it's even, I flip a coin. If it's odd, I spin a spinner. That's a dependent event because whatever happens, whatever the second thing is, depends on what happens in the first event. If you roll an even, that makes the outcome totally different. If you roll an odd, that's a totally different thing. So if it depends on the other one, that's a dependent event. Again, I think that's an official definition, but I think that so far is the easiest way. If you have a better way, please tell me. I'm always looking for new ways. Independent events, when the events are independent. Oh, that doesn't make sense. Independent affects each other. Where the events, I guess, don't affect each other is a better way to say it in that sentence. But they are independent of each other. So again, an example of that is earlier, if I roll a dice and then flip a coin, it doesn't matter what that dice does if you're just flipping a coin afterwards. If you roll a 3, doesn't matter, you're still flipping a coin. If you roll an even number, doesn't matter, you're still flipping a coin. So if the second one does not depend on the first one, they are independent of each other, then it's an independent event. So the first thing we're going to do, and you will have some questions like this on the test, go through and we're going to look at these. We're going to decide if they're dependent events. And again, this is one of them that I think is difficult until you get the hang of it because a lot of times it depends on how you ask yourself. And again, that's why I thought of the phrase, the second one depends on the first one. I think that's a very good way to look at it. There has been many times that I've gone through this with classes that I confuse myself in here. And so the best way I think to think of it, for me is, at least, is if it depends on the first one. So this one, I roll a number cube and then I spin a spinner. So does the spinner, does that outcome, does that depend on what we did in the first one? No, not at all. It doesn't matter if you roll an even and odd, doesn't make any difference. You roll a dice, then you spin a spinner. They're completely independent of each other. Now this is one that's hopefully pretty obvious. I flip a coin. If it's heads, I roll a number cube. If it's tails, I spin a spinner. Well, that one is dependent because, again, the thing that determines whether you do a number cube or a spinner depends on that first event. So whatever happens second, that depends on what happens that first event. Obviously see where number 1 and 2 go together as far as they're very similar to each other, but they're opposites. One's independent, one's dependent. And I only say that because the same thing with number 3 and 4. Number 3, I pick a flashcard, and then I pick another one from the stack of 30 flashcards. Let me see where is it. Put it over here, and I wonder if that should have been. So the thing with this one is it's going to end up being dependent. And again, this is one that I'll be more specific with, probably. One extra phrase that I should add with this one that make it easier. So this one says I pick a flashcard, and then I pick another flashcard from the stack. The thing that it doesn't say is it doesn't say you put the flashcard back. If you put the flashcard back, then it would be independent. But since you keep the flashcard and pick another one, then they are dependent of each other, because that second flashcard, let's just say there's 30 of them. Let's say they're numbered 1 through 30. If you pick one and it's number 4, then the second one you pick can't be a number 4. So that's why if you don't replace it, if you don't put that one back, it's dependent. If you would pick a card and then put it back, then it would be dependent. Now, again, this one I would say is very much fair game, because I just said I think it's described fairly well. I picked a flashcard, and then I picked another one. If I put it back, I would put it in there. I put it back and pick another one. But honestly, on a test, I'll probably specify either way. So on a test, I would probably change this one to either say I pick a flashcard, I put it back, and then I pick another one. Make sure you're on the same page, or the opposite way out as well. So like number 4 says, you select a coin at random from your pocket, you replace the coin, and then select again. If you replace it, it is dependent. So this little box there says kind of a lot of those two examples. Now again, every time if I ever replace it, if I ever put it back, I definitely always specify that. But again, I'm on a test. I don't want there to be any ambiguous. I don't want you guys to miss a problem just because you try to specify on all those on the test if you put it back or if you don't. But again, that box is key with that one. If you do put it back, it's dependent. If you don't put it back, because again, it doesn't matter what you do the first time. If you do put it back, or if you don't put it back, then it's dependent. And that's why this is confusing, because it's just so, everything's just perfect opposites, and so it's very easy to get them flipped around. You will get formulas on the test, like this formula we'll go over in a second. You'll get that on the test. You will not get, you won't get that little box that says with replacement. So that you will have to commit to your memory. So I choose a marble from a bag. I choose another marble. Again, since you kept it, you did not replace it, so it's dependent. I keep the marble and choose another one. Since you did not replace it, it is dependent. Then number 6, a number is chosen, then a letter is chosen from the alphabet. That is independent because it doesn't say anything. If you chose a number and then you choose a letter, it doesn't matter, obviously, or they're hinting at, it doesn't matter what the number is, you're still just choosing a letter. Choose a number from 1 to 10, and you said 9, and then I said choose a letter. Doesn't matter what number you picked, you can choose any letter. So that is independent. Are there any questions over those? And again, the question you always want to ask yourself is, the second one depend on the first one? And again, it does get a little bit hairy, I think, when it comes to replacing it and not replacing it. But again, the good news is you can always memorize that little box. With replacement is independent. If you do not replace it, if you keep it, then it's dependent. Hopefully that kind of makes sense, but also if it doesn't, not to be that guy, but you can just memorize that. Oh. The first thing we're going to go over is the probability of A and B. Now, the other option is A or B. So that's a whole different thing if it's A or B happening. So we're going to do the probability of A happening and the probability of B happening at the same time. So the first step, if are independent, then the probability of A and B is just the probability of A multiplied by the probability of B. Now, one thing that I always remember in math is anytime the word and, most of the time that means multiply. So the probability of this and the probability of this means we multiply together. If it's an or, that's usually adding, and we'll do that a little bit later because that's a little bit different. Now, the only other thing I'm going to go over before we start over this is probability if A and B happening if it's an independent event. If it's a dependent event, that's going to be a little bit more in detail or in depth. Unfortunately, we're not going to get into that. That is goes into conditional probability. And again, I know I said this about some other things, but if we had 2 more days of this, I definitely want conditional probability. Unfortunately, we don't have 2 more days because that's always a fun one. And when I'm asking, it means it's pretty difficult. People say, well, what if it's dependent? About that. So, what's the probability of 6 on a number cube and flipping a coin and getting tails? Now, again, first off, you won't have to do this every time because I'm not going to trick you guys. But this is a independent event. The cube doesn't affect the coin. The coin doesn't affect the cube at all. They are very independent events. So the probability of rolling a 6, that's your event. Probability of flipping tails, that's your event B. All we need to do is find the probability of both of those and multiply them together. The probability of rolling a 6 is 1 out of 6. You guys all probably know that from that last lesson we did. 1, 6. There's 6 sides total, so 1 out of 6. The probability of flipping a tails, there's 1 tail out of the 2 sides possible. So the probability of both rolling a 6 and then flipping a tails is 1 6 multiplied by 1 over 2. You can either do that in a calculator or by hand. Remember, multiplying fractions by hand is really easy. You just multiply straight across. So the probability you you roll a 6 and flip a coin and get tails, that is 1 out of 12. Again, if you want to, 1 out of 12 is 0.08 or 8%. I don't care which one of those you use. Either one is fine. To this. Now, again, if they're dependent events, there's a little bit more to it. I would really like to go over that lesson maybe next year, but this year we just don't have the time to. All right, the next one says, at a picnic, there are 10 diet drinks and 5 regular drinks. There are also 8 bags of fat-free chips and 12 bags of regular chips. If you grab a drink and a bag of chips without looking, what's the probability that the first one, a diet drink and a fat-free chip, or the next one, you get a regular drink and a regular chip? So again, just to make sure you understand the concept, you're at like a cookout and you're talking to someone as you're trying to grab food. That person wants to leave you alone. You wish they'd leave. That's usually me. And so you have to talk to them and grab your food, so you're not really looking. So what's the probability? A is that you have a diet drink. B is that you get fat-free chips. So A, the probability of a diet drink, there are 10 diet drinks. If there's 10 diet and 5 regular, there's 15 total. Try to make that a little bit bigger. And the fat-free chips, there are 8 bags of fat-free chips over a total of 8 plus 12 is 20. Now, obviously, it's not a bad idea to reduce those fractions, but if you're going to use your calculator anyways, you could just put them in. They'll give you the answer. They can reduce it for you. Your answer definitely needs to be reduced. If you answer as a fraction, definitely need to reduce that. As far as the 10 over 15, 10 over 20, you could, but you certainly don't have to. Uh, 10 over 15 times 8 over 20 in my calculator. If you do that, 4 over 15, which is also 0.27, which is 27%. Again, I don't care which way you do it. The way I do it in my calculator, I would do the 0.27, because again, in my calculator, I can't put fractions in, and so they end up as decimals, and they give me a decimal. Your calculators, if you do a fraction, that's fine. Again, just make sure your fraction is reduced. That's the big thing. Then the next one, you get 10 regular drinks and regular chips. You get a regular drink. So there's 5 regular drinks out of the 15. And there are 12 regular chips out of the 20. Again, if you want to reduce those first, you can. But also, if you're going to use your calculator, it'll end up reducing that for you. So I end up getting 1 out of 5, which is the same thing as 0.2 or 20%. You do not need all 3 of those numbers. It's the easiest for you to find. So far, so good. And for our test, if it says and, this is how you're going to do it. Other types of problems today. All right, suppose you have a bag with 20 marbles in it. So this one's nice because they tell you how many marbles are in it total. A lot of times they don't do that. So the first thing you have to do is add them all together. But that one tells you there's 20. 9 are blue, 6 are green, 5 are red. Find the probability of the following. One blue and one red with replacement. So one blue, there are 9. We took that blue and we put it back. And so the red one, there are 5 red ones out of the 20 total. So 9 over 20 times 5 over 20. I get 9 out of 80. If you do a fraction, 0.11 or 11% is what I end up getting. Now, B and C, I guess I will tell you I lied a little bit where this way when we do a dependent event. With this specific example, it's not that bad because it's not that hard to find that second fraction or that second probability. Some of them are a lot more difficult. But again, most of you guys would have done it anyways. So now we're doing them without replacement. So one blue and one red without replacement. So one blue, there's 9 blue out of 20 total. But now one red, there are 5 red, but now there's not 20 left. You never put that blue one back. It doesn't seem like that big of a deal, but that makes the chances of choosing the red one a little bit better. If you want to think of it this way, a lot of times in probability, if you break it down to its most extreme example, it makes it kind of more easy to think about. So marbles in a bag, one is red, blue one. That makes the chance of picking the right one pretty good because there's only one. If you ever want to think of it in extreme examples, you can. But again, also, if you just want to think of that, like I said, there's only 19, so 5 out of 19. Again, calculator. That one got me 9 out of 76, which ends up rounding up to 0.12 or 12%. So it's close to that other one. And this last one is even a little bit more in depth or involved, I guess I would say. You draw 2 blue ones without replacing. So now again, remember, it's way easier rather than sticking your hand in a bag and just grabbing 2 marbles. It's way easier to think of grabbing one and then sticking your hand in and grabbing another. Making it 2 separate events helps. So the first one, grabbing a blue one, there is 9 out of 20. We just talked about that for the last 3 problems. But now if you don't put it back and you pick another one, there are only 8 blue ones left, but there's only 19 total. So again, that's the hard part of that one. Since just look at what's left in the bag. There's only 8 blue ones left to choose from. There's only 19 total. So 9 times 8 over 19 ends up giving you 18 over 95, which again, for me, I would just put as the decimal 0.19 or 19%. Calculator gives me the decimal, so I think that's easier. If your calculator gives you the fraction, that's fine. For time purposes, I'm going to skip this next one. It's very similar to the other ones. Again, the biggest key with this one is says, today you grab a book and return it. Tomorrow you do the same thing. So you grab a book, but then you put that book back. So then the next day you still have all the books there to your disposal. So that's, again, very similar to the problem A where you do replace the thing. Now we're going to shift gears and we're going to get into the problem multiply for our purposes, or problems mostly you're adding, and we'll talk about the little discrepancy in a second. To that little currency, we have to know if it's mutually exclusive or not. Mutually exclusive events are events that this thing. Mutually exclusive are events that cannot happen at the same time. Now the thing, and this is the reason I had to think about this, is because the way I always remember this is mutually exclusive. The word exclusive means exclude, or sounds like exclude. And so mutually exclusive means the two groups totally exclude each other. They have no overlap. So a good example of this is if you have, let me think of a good one that has some overlap. Survey in this room, and this is apparently not as common as it used to be when I was in high school. If I did a survey and I have the athletes over here and the people involved in music stuff over here, when I was in high school, that was not mutually exclusive because there was an overlap. There was me, there was both. When you have two groups that have an overlap, they do not exclude. These are the people that do football. You can't do those at the same time, and so they completely exclude each other. There is no overlap. If they exclude each other, they're exclusive, mutually exclusive. So again, this is where I think this, in my opinion, this is why this lesson's hard, is because there's independent and dependent, exclusive and not mutually exclusive, and they're both opposites and very similar to each other. Times today exclude each other. And there's no opposite. The opposite is that they are just not mutually exclusive. Like it's not independent and dependent, that there's two words. There's just, it is exclusive or it is not exclusive. So let's do some examples of this. You roll a number cube and you roll a 2 and a 3. Well, you can't have a 2. A 2 is a 2, a 3 is a 3. They're not the same at all. They don't overlap at all. So they exclude each other. Since they exclude each other, they are exclusive. And again, that's the hard part because when I was learning this, and especially when I was teaching this my first couple years, I would say the number cubes, they don't overlap. Since they don't overlap, then they're not exclusive. One of the ways I explained it was really confusing with they don't do this, so they are this. So again, I think it's easiest if they exclude each other, they are exclusive. I think that's the easiest so far that I've nailed down. Again, if you have a better idea, I'm very much open to suggestions. That's very much, I wish I would love that, genuinely. You roll a number cube and you roll a number cube and roll an even number and a multiple of 3. So keep in mind, again, these are happening at the same time. So like the first one, you can't roll a 2 and a 3 at the same time. But this one says you roll an even number and a multiple of 3. So the other way to think of it, you roll an even number that's also a multiple of 3. Well, the even numbers are 2, 4, and 6. The multiples of 3 are 3 and 6. So there is an overlap with 6. So 6 is both an even number and a multiple of 3. So they do not exclude each other. So they are not mutually exclusive. I think that was a confusing thing. They do overlap, so they are not exclusive. And since one was a positive and one is a negative, that's what confused a lot of people. So look at it if they exclude each other. They exclude each other, so they are not exclusive. You select a card from a 52 card deck. You choose a red card and an even card. Now I should go through here and put that is also a red card that is also an even number card. That might help. But you choose a red card and an even number card. I don't know how many of you are familiar with cards, but that is very much, that overlaps. All the red cards, you have 2s, 4s, 6. You have some that are black, but also some that are red. So they do not exclude each other, so they're not exclusive. Again, the whole thing is if you can think of an example that falls in categories. So card that falls in the 4 hearts, red and even. You select a card from a 52 card deck, you choose a red card and a black card. That is mutually exclusive. They exclude each other because in a deck of cards, you cannot think of an example that is both a black card and a red card. So those completely exclude each other. Now this one's important because this one does determine on what formula you use. Kind of. So if they are mutually exclusive, if it is a probability of A or B, you just add those together. Like I said earlier, if it's and, you multiply. If it's or, you add. Or if there is an overlap, not mutually exclusive, then if there's probability of A or B, you take probability of A and add it to the probability of B, but you subtract the probability of both of them happening. That there kind of are two different examples or two different. I'll give you both of them. I always use the second formula every single time. And that was one of my battles when I started teaching this. I try to tell students when to use which one. And definitely, if you can tell a difference, you can totally choose. I will talk about that. But if you always choose the second one, the probability of both happening is just 0. So the first example, the reason it doesn't say the probability, there is no probability of both, so it would just be 0. There is no overlap, so you'd be subtracting 0. So that's how I always look at this, because I only have one formula. So let's get into this. I know yours is printed out in black and white. That's why I kind of labeled these with letters. But if you look at that little tray, I guess, at the side, we have different colors, but we also have different shapes. So we have an orange circle, a yellow triangle, a red circle, a green square, a green circle, orange square, red circle, red square. That's what the O's, Y's, and G's stand for. Shapes. So suppose you reach into the dish to the right and select a token at random. What is the probability that the token is round or it's green? Again, technically, on here we should decide if it's mutually exclusive or not. So double check, is there anything that is both at the very same time? Is it both round and green? So round and green, yeah, we have these two. Those two are both round and green, so they do have so they do not exclude each other, so they're not mutually exclusive. Now again, like I said, I'm going to teach you how to do it both ways, but really, if you just always stick to that second formula, it'll work out, and I'll show you in some of these other ones in a second. So if you follow that formula, what's the probability of A happening? Probability of round. Well, there is 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 total things over there. So the probability that it selects a round one, how many are circles? 1, 2, 3, 4, 5. Actually, 1, 2, 3, 4, 5. 5 of them are round out of the 9 total. How many are green? Well, those are the ones that are labeled with the G. 1, 2, 3 that are green out of the 9 total. So we would add there, but we have to subtract. Now this is the hard part, that I don't think it's that bad. You just have to make sure you kind of think about it, and you have to get used to it, get practice with it. What's the probability of both happening? One that is both round and green. Well, I circled the overlap earlier when I was talking about exclusive or not. I circled the two that are both green and round. There's only 2 of them out of the 9 total. There are 2 that are round and green out of the 9 total. That's the formula you use. Now, the good news is, since all of them are out of the total, they all have a denominator of 9, so technically they all have a common denominator, so it's not really that hard to take 5 plus 3 minus 2. But also, you can use your calculator. So 5 plus 3 is 8, minus 2 is 6. So you end up getting 6 over 9, which you can reduce down. So I got 2/3 for that, but you could also say 0.67 or 67%. All those are fine. That's the difference. That's the hardest part of today. Knowing that there's an overlap and knowing how to find that overlap. And again, I did it on purpose. It used to be formula I've seen before. Over here says probability of A and B, and I think it's easier to think of, rather than probability of A and B, thinking of the probability of both of them happening. The probability of both, round and true. So let's move on to the next one. A token, so the probability you pick a token and it is red or orange. Well, this one, are there any that are both red and orange at the same time? There aren't any. They're either red or they're orange. So this one is mutually exclusive. They completely exclude each other. So technically, you're going to use that first equation. But I'm going to show you where if you use the second equation, it's going to end up as the same thing. And so I always use that second equation. So what's the probability of red? There are 1, 2, 3 red ones out of 9. Or, so I have a plus. Probability of orange, there are 2 orange ones. 2 of them have an O on them out of 9. That's the formula. If you got confused and used the wrong formula, it's okay, because if you subtract the overlap, what's the probability I pick one that is both at the same time, red and orange? There's none. So that's why if you don't know which formula to use, always just pick the second one, because they really are kind of the same one. It's just one of them has no overlap. So always pick the second one if you don't know. But that's the reason, because it's just going to be plus 0 over 9, which is 0. So 3 plus 2 is 5 over 9. That's already reduced, so 5 over 9, which is the same thing as 56%, or 0.5. And the next one, same thing, a token is round and red. So which one, or is it possible, is a good way to say it, but it's also good to notice. Is it possible they have one that's both round and red? Well, yeah, it is possible, because if you just look, you can see those. This one's round and red. This one is round and red. It kind of helps to circle those that are both, because that'll help this one as well. But since there is an overlap, they do not exclude each other, so they're not exclusive. So what's the probability that it's round or red? Well, if it's round, there are, we just did one that was round, what, 3? Oh, no, 5. 1, 2, 3, 4, 5. Sorry, I was, okay. Red, there are 3 red ones over 9, but we have to subtract the overlap that are both red and round, so you subtract 2 out of the 9. That ironically ends up as the same exact math we had before. That is 6 over 9, which is 2/3, or 0.67. Last thing I will say with this before I move on, and I might put one like this on the test, because if you are being careful, it's a little red flag you get wrong. But you end up with a problem where your numerator is bigger than your denominator, that means the probability is wrong. Because remember, if the numerator is bigger than the denominator, the probability is going to be 1 point something, which means it's over 100%. It does happen occasionally with these problems overlap, and sometimes if you forget to subtract the overlap, you end up with a problem that's like 11 over 9. So that's a good way to double check to make sure. Again, for me personally, I just always use that second formula. That way you always kind of remember, worst case scenario, there is no overlaps, so you're going to get 0. Now, I will tell you, on the test, you will have questions like this, except for it'll be separated. You'll have questions that ask if it's exclusive or not. That'll be one question. Then you'll have another question that just tells you to find the probability. So if you were confused at this part, but you understood how to use the formula and get the answer, again, there will be multiple choice. There will be some questions like that, but they won't be the same. They won't be all grouped in the same spot. Which, I don't know, maybe that's not good. Okay, number 2 is a really good one, because there's one small thing I want to make sure you remember this one, and some of you guys would figure out this mistake if you did it on your own anyways. So students choose one elective each school year. About 18% choose woodworking and 38% choose music, or chose music. What's the probability of students choosing woodworking or music? Now here's the thing that helps with this one. You have to read it carefully. You have to choose one elective. Because I know some of you guys are like, yeah, you could obviously you could do woodworking and music. Some people are doing that at Fairfield right now. They're doing a woodworking type class or building trades type class, and they're doing music. But this one is saying you only choose one elective, so you cannot choose both. So again, there is no, they exclude each other, so they're exclusive. Here's the problem that a lot of people do. Oh man, did I not do any of those up here? That's the difference. Huh, okay, didn't think about that. So you're going to want to, anytime they give you percentages, you're going to decimals before you get to them. We're back and forth. It says if you multiply, it's a huge difference. If you add, it's actually not a difference. If you took 18 plus 38, it's not the end of the world. But if you multiply, it definitely is the end of the world. So 18 plus 38, 56. But again, for me, I'm going to do 0.18 plus 0.38. That's going to give you 0.56, or you can make it 56%. Adding is not that big a deal, but if you're multiplying, I know this question will be totally wrong, but it said, what's the probability that a student does woodworking and music if you can multiply those together? 18 multiplied by 38 gives you like, basically you just have to remember to move decimals around. 8%. So if you multiply, you definitely have to make sure you move the decimal before you actually multiply. With adding, it's not that big of a deal. I'm pondering if I want to stop there and let you guys work on your homework. We'll do number 3, and then we'll end on that one. So the numbers 1 through 10 are written on index cards and placed into a box. What's the probability that a card chosen at random is even or has a number that is greater than 7? So is there any numbers that are even that are also greater than 7? So one way to do this is you actually could list them out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The even numbers I'm going to underline 2, 4, 6, 8, 10. Those are even. The numbers bigger than 7 I'm going to circle. That's 8, 9, and 10. Are there numbers that are both circled and underlined? Yes, there are. So they do not exclude each other, so they are not exclusive. I know list them all out like that, but sometimes it kind of helps. So what's the probability for greater than 7? So the probability of even, there are 5 out of the 10 that are even. Probability that's bigger than 7, there are 3 out of 10 that are bigger than 7. And the overlap is there are 2 out of 10 that are both bigger than 7 and even. So again, if you want to reduce your fractions beforehand, you can, but it's kind of easier not to if you're adding, especially if you're doing it by hand. 5 plus 3 is 8, minus 2 is 6. Over 10, make sure you reduce that. That's 3 over 5, which is 60%. Pretty straightforward. They're either born in Indiana or born in Michigan. You don't rarely have someone born on the Indiana-Michigan line, as in that does happen, doesn't really exist. Actually, I just watched a documentary where the exact Michigan-Indiana line is actually not set in stone, so it's very probable. Good. Again, there's no exit ticket for today. Make sure you still do your worksheet. I think that's very beneficial to you guys. Especially in this one, so have me apologize that I gave you an exit ticket, but I know that's probably a relief for some of you. Tomorrow's our last lesson. There will be, or hopefully will be, an exit ticket for that. I will get you guys your practice test tomorrow and get your quizzes graded as soon as I can.